wanted to see the code. Okay, so as I said, we will start with, okay, so we will start with a simple architecture where we will come across only one input, one output, or maybe with one hidden layer. So that we will see as a first case the MATLAB code. But later, as I said, when you handle in the form of a vector, you can handle input output of any dimension. Only thing is the learning process will take more time. Okay. Now, so when we talk about the algorithm, what we are going to discuss, there will be like three phases. Okay, one is called as many of you might be aware of. I'm just repeating it for the understanding purpose. Okay, so there is going to be a feed forward phase where you will apply the input patterns and then try to again, like we know that the basic operation what I've discussed earlier, what is happening inside the artificial neuron. Like every neuron will receive the weighted sum of inputs that will undergo an activation function, and every layer you will choose a particular activation function that will undergo an activation function to give you a net final output. Net input will enter into each neuron that will undergo an activation function to give us a final output. So the final output from each hidden layer again will be multiplied by the associated weight that goes as a net input to the neurons in the next higher layer that will undergo an activation function to give us a final output. So initially we will start with the random values of weight vectors. We will try to compute what is the actual output we are looking for from the neural network. And we know that because we have chosen the initial value of weights, okay, like randomly we have chosen, whatever output I am getting from the neural network will not match with my target or label output. So I'll try to compare how much is the actual output I am getting from the network and what is the desired output or what is the target output. Okay, there is going to be a difference. Okay, so this difference is basically called as error in the output layer. Now, this error in the output layer is going to be used for updating the weights, okay, of the output layer neurons. And then in the backpropagation algorithm, the objective function for the backpropagation algorithm will be minimization of sum of square of all these errors. So that means when you come across M outputs, elements in the M output, that means you will have M errors, E1 to EM. You wanted to take the square of all the errors. So total error, you wanted to minimize it. So that means this error E1 will have impact in deciding. Okay, that means this E1 will be like by updating the weights, connecting the weights coming from the hidden layer into the neuron one. By properly updating them, I can minimize this error. So that is a basic idea. So that means the weights are going to be updated as a function of how much is the error we are getting in the output layer. Okay, so that means again this error. Okay, so this error. So that means we wanted to compute the actual output from the network, compare it with the target output, compute the error, then try to backpropagate the error information. So that is the reason this is called as backpropagation algorithm. And this error will be backpropagated. So errors of the output layers will be used for updating the output layer weights, which are getting connected to the output layer neurons. And then we will try to backpropagate the error. So we will try to find out what is the rate at which the individual error can be minimized. That means DOE with respect to W of each layer. Okay, we wanted to minimize that. So we will try to find out the error gradient, and based on the function of error gradient, okay, by updating the weights in the negative direction as that of the error gradient, we will try to minimize this error. So that is the basic idea with which backpropagation algorithm is working. So you wanted to update the weight. So that means the objective function for the backpropagation algorithm is minimization of sum of square of error. And different learning algorithms will have different functions of error. So that means the objective function, what is it we wanted to minimize, may vary from algorithm to algorithm. So you need an understanding on that. Accordingly, the weight update logs has been derived. So these weight update logs have been derived in order to minimize this error. Okay, we wanted to move in the direction towards minimization of error. So with that objective, we try to update the weight. So we wanted to use a systematic procedure so that my output of a neural network will be moving towards the target output. So that is the idea with which we are working here. Okay. Now let me go to the other presentation now. So this is a basic idea. So now let me start with the simple example first, the code for the simple example. And then let me go to the backpropagation code. So when we discuss the backpropagation code, we will also see the backpropagation algorithm, little bit of understanding. Okay. So that is, I have not taken the complex maths behind the backpropagation algorithm. I will be limiting myself only to whatever is required for understanding the backpropagation code, which we wanted to develop it from the scratch. Okay. So that part only I'll be just making use of it. Okay. So let me go to the next content, which will help you to understand the vector representation. Okay. So this is again, this content I have taken from the net only, from the MATLAB I have taken, because I wanted you to have a thorough understanding on vector representation, because in our MATLAB code, we will be like using only this vector representation. Okay. Now here we see a single, okay, this is going to be again a single neural network. Okay, a single neural network. So what we see here is like the capital R. Okay, so here everything is vector representation. So R represent the total number of inputs we have. Okay, so that is the P, the size of P vector is R by 1. So R refers to number of inputs. Okay, and P is the vector, input vector. Okay, so this input vector is going to be multiplied with the associated weight vectors. Okay, associated weight vectors. Now, if you see the size of the weight vectors, as I said, like we wanted to multiply the P, which is an input vector, with the corresponding weight vector, we wanted to multiply it. Okay. Now, again, coming to this weight vector. So here we consider a case where we come across the number of output as equal to S. So there are S number of outputs. So here we see a single layer, okay, single layer in which there are R inputs which are entering into the single layer, and there are S outputs which are leaving the single layer. Okay, so S is the number of outputs. So this A is a vector which represents the output here. Okay, the output, the final output which we get from a single layer neural network. The vector size is going to be S by 1. Okay, so R by 1 is a vector size of input. There are R elements present. The corresponding vector is represented by P. A is the output vector, which has got a corresponding vector size of S by 1. There are S is the number of outputs. Okay. Now, when you wanted, what is the relation between A and this P? Okay. Now, as I said, like these weight vectors, okay, this weight vectors, so how many neurons which we will have? This output layer is going to have S number of neurons, because S outputs you wanted to generate. There will be S number of neurons. So this is only a simplified schematic representation. It is not the detailed neural network architecture. It is a simplified representation, which basically is represented in the vector form now. Okay, so the like this SY1 basically means that there are S number of artificial neurons. Okay, and this F is basically the collection of S number of activation functions. It is F is again a vector which has got S number of activation functions. Okay, and this F could be like a log sigmoid, or it could be a tan hyperbolic function, anything like that. Okay. So, okay. So now because you wanted to generate S outputs and there are R inputs, okay, the corresponding vector, okay, weight vector, which is connecting the input with R inputs with S output layer neurons, will have the size of S by R, will have a size of S by R, okay. Now, why do we represent as S by R? Because as I said, like we wanted to properly handle them when we perform a weighted sum of input. So when we say weighted sum of input, as I said, what is the basic operation we wanted to perform? W multiplied by P plus the bias term, as I said, which will have a constant input of 1, constant activation of 1, P multiplied by 1, W multiplied by P. This will be added together. So WP plus B is going to be the some weighted sum of input, which is nothing but a net output which is coming out. That will undergo an activation function F to give us A, which is the final output. Okay, so here we see, like we can find out a product between W and P, provided W has a dimension of S by R and P has a dimension of R by 1. So the product will have a dimension of S by 1. And B bias has a dimension of S by 1. So S by 1 added with S by 1, you will get S by 1. And again, that will undergo individual activation function to give us S by 1 as an output. So you have to cross check whether the matrix are matching in order to perform. Otherwise, you will have a dimensionality error. Okay, so this is basically simple case where we wanted to represent in the form of a vector. So in my MATLAB code also, I'll be handling, okay, for a basic scratch backpropagation algorithm, which can be extended for a deep kind of network also. For modeling of any function, any system, we will be handling all these vectors. Okay. So this I thought will help you to understand. Okay, so this is one thing. This content I have taken only from the net. Okay, I'm just stopping the presentation. Then we will go to the MATLAB code. Okay. Okay. So can everyone see my MATLAB code? Like, okay. Yeah, Sudha, can you give a feedback? Can everyone see my MATLAB code?
Yes, ma'am. Yes, ma'am.
Okay, okay. Yeah. Yeah. So like if again like okay. Okay. Yeah. So this is, as I said, like here we are going to use a neural network toolbox. Okay. So this is like anyone can do it. Yeah, so anyone can use this neural network toolbox and very easily develop a model or easily approximate any function for any engineering application. Okay, so the benefit of using the neural network toolbox or neural network built-in M-file commands for neural network is like your development time can be very much reduced. And the second point is that all these codes have been thoroughly, it has been verified and it has been checked properly, validated. So there will be no error with respect to the coding part. And only thing is like without knowing what is happening, how the algorithm is working, you will be using it as a black box. That is a problem here. And the parameters of the algorithm, you will not know how to properly choose it. Okay. Now, as far as the code is concerned, there will be default parameters. So you will be mostly using the default parameters, where there are options for changing the parameters. So whenever we wanted to use a neural network toolbox, we should be able to configure the parameters properly. That is the intention here. So let me see the simple example, okay? Now, with respect to neural network, what is it we have to do? Like we have to, first of all, we have to configure the neural network architecture. We have to decide on the architecture. Do I need a single layer or do I need the many layers? How many hidden layers I'm looking for? How many neurons in each layer? So first of all, you need to declare the neural network. Architecture of the neural network, you need to declare that. Then you need to identify, whenever you wanted to use a toolbox, you need to choose a proper learning algorithm. And the third point is like the parameters. If you wanted to choose the parameters, like now as far as the neural network is concerned, there is a learning phase. You need to specify when to stop the learning process. Okay. Because what we are discussing is a supervised learning, because we are focusing only on the supervised learning now. So like you need to specify when to stop the learning process. You need to specify the termination criteria. So when to come out of a learning algorithm. So this is what is very important. Okay. Well, as I said, like here I'm handling the inputs. Okay. So like if you see this input, okay. So these are all the basic commands, first few lines. So here it is basically a mapping problem where we want to map an input pattern with the corresponding target pattern. Okay. Now in this example, so this is an example with a single input, single output. Okay, so what does it we see here is like the input, what we are considering here. So this is a MATLAB command to choose the input in the range of -1 to +1 at a rate of 0.1. So that means every 0.1. So you will have an input for every 0.1 ranging from -1 to +1. Okay, so that many number of inputs will be present. Okay, and correspondingly, you will have the corresponding target. And this target will specify for each input. Again, if you see here, we try to represent in the form of a vector. Okay, so that means the input is going to be when you try to imagine related with the example what we have seen, this input will have a size of r by 1. The target output will have a size of s by 1. Okay, so if there are s number of output that you wanted to generate. Okay, so this many number of input output will be present. So, but this, sorry. So this is an example where we consider only single input and single output. Okay. So for each value of input, for example, when the input is -1, I am looking for -0.96 as an output. Okay. When the input is like -0.99, I am looking for -0.577. So you have to change from -1 to +1 at a step size of 0.1. Okay, at a step size of 0.1. So keep adding 0.1. So the first input data will be like -1. The second input data will be -1 plus 0.1, which corresponds to -0.99. 9. Okay. So, and then with the -0.9, you add another plus 0.1. So that means the third data will be minus 0.8. So like that, you will have a data and the corresponding target outputs are given. So that means for a supervised learning, you are given the training table or the training patterns are given. So you are given an input pattern and the corresponding target pattern is specified to you. Okay. Now, as I said, like I have to configure a neural network. So I need to declare a neural network. Here I'm using a neural network toolbox. Okay. And this is a toolbox in which we wanted to use a feed forward network. Okay. So feed forward network is a neural network toolbox command. And this file refers to, so this is basically feed forward network. So you can just search through Google. You will see that this network is a single layer network. Okay, so that means in this application, we have got one input, one output, and there are this 5 refers to number of neurons we will have in the hidden layer. So the architecture is going to be 151. So that is architecture that. So I'm configuring a net, I'm declaring a net, which will be a feed forward network. Once you call this command, the corresponding net is going to be configured. Okay. Now, what are the additional parameters I'm looking for? Okay. Now, this additional parameters I'm looking for is like how many epochs. So applying all the input output patterns once to the network in neural network terminology, we call it as an epoch. So here the number of epochs is like when it reaches 1000, or when you can also specify the error limit. How much is the limit you're looking for? Do you want an error of like 0.0001? So when either epoch is reached or the limit is reached, the neural network learning will come out of it. Algorithm will come out of it. Okay. And again, you can configure like what is the activation function you want for the input layer, activation function you want for the output layer. Okay. Now here for the hidden layer, we know that the input layer does not do any computation as far as neural network is concerned. Only the hidden layer, there is a computation which is happening. In the output layer, there is a computation which is happening. In this case, like a radial basis function is used for the hidden layer neurons activation function, and the activation function used for the output layer is a pure line activation function. You can view this particular network. So when you put this network, the network with one neuron in the input, one neuron in the output, and 5 neurons in the hidden layer, with this activation functions will be like declared or will be configured. Okay, so now configuration is over. So I have got the training data, I have configured the network. So all these codes I'll share with you. So I request you so to change this input output patterns based on your application, and then try to run the code. Okay. And then try to just check whether you are able to get a proper output. So I'm going to run and show you the output for this code also. For this example, I'll be running and showing you the output. Okay. So now configuration is over. What is the next step? Like we have to train the network now. Okay. So for training the network, so network is going to be trained by calling this net and input pattern and the corresponding target pattern. Okay. So the default general net, okay, the learning algorithm used for general net default is like train LM algorithm, okay, which is one of the popularly used learning algorithm with respect to back propagation. That is an improved and like modified version of the standard back propagation algorithm. So when you say net, it is a train LM algorithm. Algorithm is used. So as I said in this example, we will not know how the train LM algorithm is working. That is hidden to us. Like a black box, we are going to use it. Only thing is like your development time will be very less. But if you write the code for train LM, it may take months for you to rectify the code, to troubleshoot the code. Okay, that is advantage here. Okay, so now, so after the training is over, so our network is ready now. So net is going to have a net, the trained network. So output of this training is going to be transferred to this net. So net is basically the output. So now what we wanted to give the input pattern and test whether we get a proper output or not. So apply here, we are applying the same input pattern. So actually like the other speakers have discussed, okay. So we need to split the data into training data, testing data, validation data, and then we have to apply, okay. So whenever you wanted to test and validate it, you have to apply a test pattern, which is slightly different from the training pattern. So I strongly recommend the participants to generate one more test data by adding a small variation to the training data and apply the test data and check whether you are able to properly get output or not. So I strongly recommend the participants to do that. And also you can keep varying the all these. Okay, so like activation function, try with other activation functions, and then try with the less number of epochs whether it is getting converged or not. Here 1000 is only randomly chosen. So some of the parameters of the neural network we try to choose them only on trial and error method. Okay, and then it is transferred. So finally, when you wanted to read the weights and biases, there is an option to get back the trained weights and trained bias values. You can transfer that to weight and bias, and from this particular workspace command you can get the corresponding trained weights also. And then we are trying to get in the form of a, now we wanted to plot it. Okay, see, plotting is like the MATLAB is a wonderful tool where you can plot all the responses in a very beautiful way. Only thing is you need to write a proper plot code for that. So writing a plot code is very, very important to get a beautiful meaningful figure in MATLAB. Okay, now this example, the code is very simple code, but later example I'll show you like how beautifully you can write a small code in MATLAB and get a very beautiful plot out of it. Okay, so we are calling a new figure. Now we wanted to plot the input pattern. Okay, so here the input pattern, the plot command shows like input pattern, you wanted to plot it, and the corresponding target pattern is going to be represented by an asterisk here. Okay, and so what we here the input pattern basically means that the pattern that is used for the target pattern that we wanted to get it is going to be matched with the actual output pattern we get from the trained network. So this the slash basically hyphen basically are the what we have used for training, the target or labels, and this asterisk represent what is the actual output we get out of the trained network. So we are going to run and show you this output. And X label I wanted to add observations, and Y label I wanted to say like a hyphen represent the neural network output and slash represents the target output. Okay, and then like figure. Okay, so again we wanted, so the how the neural network weights are changing, we are trying to plot it using one more figure we are trying to plot it. Okay, okay, so like if there are any doubts with respect to code, maybe like during discussion. Okay, now I'll not be able to spare any time, but maybe towards, because there is one more algorithm which we wanted to cover up, so I'll just quickly run and show you the output. One second. So I need to share with you the new screen. Okay. So there are some questions in the chat box which I'll try to answer later. How to choose the initial value of weights. Okay. I think the second examples, once we discuss that, I think you will be able to understand that. Okay. So like, let me go to that. Okay. So this is the kind of, as I said, like this is a kind of architecture that we have created. Okay. As I said, like there are 5 neurons in the hidden layer, and there are going to be like 1 neuron in the output layer. Okay. And let me show the result part, because this is a MATLAB we are running it. I'm not able to simultaneously show the result. Okay. So this is the result part. So can you see the result now? See how beautiful it is like. Okay. The data. Okay. The observations versus the corresponding. Okay. The input versus the corresponding output. How beautifully it has come. You see the input observations which are in the range of -1 to +1. Okay. The input in the range of -1 to +1, with the sample taken at a step size of every 0.1. Every 0.1, we see the okay. So like here we see one blue, and then there is the asterisk here. Asterisks represent what we get from the here it is a target output, and the blue line is a neural network output, trained neural network output. Okay. So this is for a simple example. So I strongly recommend you to try for your example. Okay. So this, yeah, test results. Somebody is asking for a test results. So right now I do not have the test results, but like the data can be varied. Okay, maybe what I can do is like, I think now time may not permit to change me some of the data, and again because we need to create one more vector, test vector, and then we have to give a test vector as an input. Okay. Maybe one thing I can do, one thing, yeah, once again, I'll try to change some of the data, and then I'll try to show you, because one has asked. Okay, you will be curious to know. So let me try to change that. Okay, and then try to run it again, because that is more important. MATLAB. Validation, once again, yeah. I'll try to change some of once again. Okay, so let me change this Y. Okay, so like what is the value? So instead of 0.96, okay, can it give 0.99 is my output? Okay, and no, sorry, not. Okay. So that means I have to change on the input once again. I have to change on the input. Okay. So instead of -1 to, there may be some issue actually, like 1 second. Can it change between 0.1 to 0? Let me add for every point, not 1. So this is the input pattern.
Ma'am, is it possible to write a separate Command line for testing, ma'am.
So the once again, just wait it. I cannot take much time. So I'm
Okay.
just skipping the training part. I'm just
Okay.
skipping the training part. Participants, can you appreciate it now? I'm giving a different input now. Okay, instead of -1 to +1 range, I'm giving a different range now. Okay, and I wanted to test my output now. So like, so we have trained it for -1 to +1. I'm using a small range within that. So let me only, I'm just skipping the training part. Then I wanted to just run this part. Okay, so let me run this part. Let me, okay, so let me run this. So I have run it once again. So let me show you the plot actually. Yeah, there may be a small issue, I think, yeah, because the input pattern is different now. The target, we have not changed the target. There may be a small issue. Yeah. So now I'll share you the new result once again. Yeah. New result. Okay. Because every time I need to go for that. Once again. Here is that result. Okay. So can you appreciate it now? Now, what is the range you see? X-axis you see? So instead of -1 to +1, my new range is -0.1 to +0.1. Okay, see? So that way, like you can also try for different ranges, -5 to +5. So all that can be done. So that is the exercise I'm giving every one of you to try it in the evening. So anyone who is facing the difficulty, maybe we will address that tomorrow when we find some time. Okay, I'm just stopping it here because we need to cover one more algorithm. Okay.
Ma'am, is it possible to determine the error, ma'am? Error value, prediction error, or this?
Sudha, wait a minute. I'll answer all the questions later. I do not have time to complete.
Okay,
But
ma'am.
yeah. So we will go to back propagation because that is important for deep kind of architecture we are going to discuss. Okay, so let me go to that. Okay, so let me go to my presentation. Where is my presentation? Yeah. Very quickly, okay. So as I said, like this max is required in order to understand the code for like how to write the backpropagation code from scratch. To understand that this small max is required. So many of you might be aware of this max. So here I am considering like there is a hidden layer and there is an output layer. There is one hidden layer and there is one output layer. The weights connecting the input with the hidden I am representing as like X is the input and Y is my output. Z are the hidden layer neuron outputs, and Wij is the input connecting input with the hidden. Wjk is the input out weights connecting the hidden with output. So it like weighted sum of input undergoes an activation function to give us Y in J, net output of the hidden layer. That okay, undergoes an activation function to give us a final output Zj. That Zj multiplied by the corresponding weights will give you Y in K, which undergoes an activation function F to give us the net final output. Okay, so the activation, like the objective function which we wanted to achieve in backpropagation algorithm is Tk minus Yk, the whole square, we wanted to minimize it. So as I said, the weights are going to be updated in order to minimize the error gradient. Okay, so how the error will be changing. So when we talk about the error gradient, the physical meaning for that is like change in error when I change Wij. How much is the change in error when I change Wjk? So Wjk is for the output layer, Wij is for the input layer. So I'm trying to get a weight update law, which weights I wanted to move in the opposite direction to that of the error gradient so that my error will get minimized. I'll move in the direction of minimization of error. So I want an expression for dou E by dou Wjk, dou E by dou Wij, wanted to get an expression. Okay, this is a very small max. So just you need to derive it. So you need an error gradient. So this is a gradient. So this is what we called as like F dash with respect to the activation function, and that will be multiplied by the corresponding net outputs also. So like first of all, we need to find out the error gradient for the output layer. then that error gradient need to be back propagated to the hidden layer. You can have more number of hidden layers. So these terms, we call them as error correction term in back propagation, like delta K and delta J are the error correction term. Delta K is the error correction term for correcting the weights of the output layer. Delta J is the error correction term for correcting the weights of the hidden layer. So you need to get formula. So that means the weight update term for the output layer will be different from the weight update term for the remaining hidden layers, because you need to use a chain rule. You need to back propagate the error gradient so that the weights can be appropriately updated. Okay. So for the output layer, we want dou E by dou W JK. Dou E by dou W JK of E. E is objective function. Here for simplicity, we have added this half here. So half of this error we are taking. So that we wanted to differentiate with respect to WJK. We know TK, which is target, will not change with respect to weight. Whereas this YK, which is a net output, will change with respect to weight. When you change weight, net output will change. Net output is nothing but f of y in k. Okay, sorry, final output will be net of f of y in k. Y in k is a net output. And expression for y in k will be like wjk multiplied by the corresponding hidden layer outputs. So you try to, this f, when you differentiate it, because you wanted to differentiate with respect to wjk, tk is not changing, whereas f of y in k is changing. So you will take this tk minus yk the whole square. When you differentiate it, it will become 2 times. So 2 and 1 by 2 will get cancelled. You will have like tk minus yk and try to differentiate. Okay, so try to partial differentiation, try to differentiate tk minus yk. Tk is not going to change. Like yk, when you differentiate it, which is nothing but f of y in k, the differentiation will be like dou by dou w jk of f of y in k. So f, when you differentiate it, it becomes f dash of y in k. Dou by dou w jk of only y in k. Y in k is nothing but your Zj multiplied by the corresponding Wjk. You are differentiating with respect to Wjk, you will have only Zj present. So what is that we have to see is like, forget about all the derivation. There is an error correction term for the output layer, which is a function of the final layer error. Okay, the error between Tk minus Yk and f dash of Ynk. So I need derivative of activation function. So this is my error correction term for correcting the weights of the output layer. So I need this. So how I am going to update the weights of the output layer? That will be nothing but minus alpha times delta k into Zj. Okay, delta k into Zj, because delta k is equal to this. Delta k into Zj is your dou E by dou Wjk. So you get this weight update loss. So now what is that we have done is, in a backpropagation algorithm, we have derived a weight update law, which will ensure you to go in the direction towards minimization of the objective function. So the objective function, depending on application, can be a minimization problem or it can be a maximization problem. Because it is a minimization problem, we move in the direction opposite to that of error gradient. If it's going to be a maximization problem, you wanted to maximize it, this will be a positive here. So you need to formulate the problem and you need to derive a weight update law. So there is the faculty and research scholars who are available here, you can propose your own weight update laws by changing the objective function. You can formulate an objective function for your problem. It can be multiple objective. There are a lot of scope for that. Okay. Now here we have taken only minimization of square of error and objective. You can also propose a weight update law in which you can take different function of error. Need not always be only the square of error. It can be any function of error. And so like even least square algorithm can be used for weight update. So different learning algorithms can be used. Like you can use a least square method. You can use like a Kalman filter, Kalman algorithm. You can use it for updating weight. You can update the weights using like genetic algorithm. There are that means it becomes like a hybrid. Okay, two different techniques, tools, you can combine them and you can show that with the proposed modification, you are aiming for some kind of an improvement. Okay. And you can also, the researchers also can come up with your own activation functions. Okay. And you will be able to publish in a very good journal if you can prove that the proposed activation function, new function. So the activation function can be any function. Okay. So you can come up with new functions and you can publish in very good journals by doing some modification in the weight update laws, by doing modifications in the algorithm that is used for weight update, by changing the updative function, by changing the activation function. There is a lot of scope for doing that. Okay. And so this is first part. The second part is like we wanted now back propagate this error gradient to the, now we are in the output layer. Now we have to back propagate it to the previous layer. That is layer which is connecting input. In this case, it is only one hidden layer. That means we need to have for the previous layer, that is nothing but the hidden layer. Okay. Now in this case, there is only one hidden layer. So you try to get the error gradient. So how error is going to change when I change Vij? Okay. We know that any change in Vij connecting input with the hidden will have impact on the net output of the hidden layer, final output of the hidden layer, and which will be multiplied by the weights of the output layer. That will have impact on the net output of the output layer and the final output of output layer, which in turn will affect your error. So that means there is a chain reaction that is happening. One point when you give a change, that gives a change in the final output we get from the neural network. So similarly, what is the impact of changing Vij on the error? So you want an error gradient for that, DOIE by dou Vij. Okay. So when you do step by step, okay, and there is a very beautiful e-book, okay, like Fundamentals of Artificial Neural Network by Lauren Fawcett, which will explain you the standard backpropagation algorithm step by step. All the variations you have in the algorithms have been very neatly explained with all numerical examples. So you will get a feel only when you work with an example, you will get a feel of that. Okay, here we see that for updating Bij, I'm having delta J. So like when you derive it, you will get this expression. I'm just skipping it for want of time. And by using this chain rule, okay, so we got this delta J, which is an error correction term between the hidden and input. And this term also error correction term, we see we have got delta K, which is error correction term for the previous layer. And I also need f dash of the hidden layer activation function. So I need the derivative of the hidden layer activation function, which I will be using it to get compute delta J. So that means you need to compute all the error correction term for all the layers. So that is the second phase of backpropagation algorithm. Then once you know this error correction term, you will be updating the weights using this weight update loss according to the backpropagation algorithm. So now what we are going to do is like, we are going to implement these steps. Okay, you forget about all the remaining thing. Try to understand only these points. Like try to remember your this term. Okay, try to remember how to get a net output. That will undergo an activation function to give us a final output. And then try to remember this particular part in order to understand the code. And then what is required, like there are two error correction term which we have to compute it. So we need this. I need error, I need derivative of error. The derivative of error in the code, you will see that I am going to explain you with the tan hyperbolic activation function. The corresponding f dash is given by 1 by f of x square. So later we will see that. So once I have got this error correction term, I am going to multiply it by eta or alpha, the learning rate, and zj or xj, which are nothing but the corresponding activation function. So zj is activation function for the output layer, activation for the output layer, or nothing but the output of the hidden layer, and xj is the activation for the hidden layer, or nothing but input for the hidden layer. So you need only this term. So once delta k, delta j's are available, I'm going to multiply it by the corresponding outputs from the previous layers. Output from the previous layer. So you need delta k, delta j. So only delta k is challenging. Only for the output layer it is simple. But when you back propagate for the other layers, so you need the derivative of activation functions of the every layer is required in order to get the corresponding weight update loss, in order to get the corresponding error correction term. So this derivative of activation function becomes challenging in order to make the backpropagation for deep kind of architectures where we aim for many number of hidden layers. And this is a basic principle. So let me go to again the MATLAB code. I think we have got very less time. Maybe another very quickly, okay. Okay. So let me come to, okay. So here I'm using it for, okay. So there are two codes, okay. One is like the general code. Other code is the backpropagation training algorithm that has been implemented for a three hidden layers. So this is an example where the code has been customized for 3 hidden layers. So like this itself is a deep kind of architecture. Okay, the literature says that when you have total number of layers as 3 and above, including the output layers, input layer, when you have more than 3 and above, you can call it some kind of a deep architecture. So deep neural network is a deep architecture with many number of hidden layers. Okay. So here we come across 5 layers, 1 input, 1 output, 3 hidden layer. So this itself is a deep kind of architecture. So we are going to see how the deep neural network, you will be able to train it using traditional backpropagation algorithm for a supervised learning, for a supervised learning applications, or for a some kind of a supervised applications. Okay, maybe a classification application or a regression application. So the application which we come across. Okay, so let me just give a small intro for the application. Then we will go to the backpropagation code. How, like, from a scratch the code has been done. So once a chain rule you are able to appreciate it, you do not need the MATLAB M-file code for backpropagation. You can write your own code. Okay, so this is application here. So in this application, like as I said, we have taken an application where we wanted to simulate it for time of simulation is 1000. Okay, then I have taken my sampling time as here every 0.25. So here we see the number of samples which we are considering is like the k is going to have a value, instances. Okay, is going to have a value from 1 to t by 4. T is 1000, so 1000 by 4 is going to be 250, and the step time is 0.25. So you have got a step time. So k will take a value from 1 to 250, and there are going to be 4 samples for every 1 to 2. So that means 1.25, 1.5, 1.75, 2.25. So like that, you will have, like, between 1 and 2, you will have 4 samples present. Okay, so that is the meaning for this. And we start from 1 to 250. So what we want to do is, like, U is the input. Okay, now again, as I said, like here I have taken an example for simple understanding, a single input, single output. But this U could be many input, many output. So this is a generalized code which can be applied for to any complex system with any number of input. Okay. So here we consider only single input. So the input which is entering into is going to be a sinusoidal function. I'm going to generate an input. So instead of the previous example, we gave this U and Y. So instead of we giving U and Y, here U and Y are generated. Okay. So U is the input, that is the sinusoidal function. So for every value of K, you try to generate the U. So you will have, depending on how many K values are there, that many number of U values will be present here. Okay, so U is only single input, but it has got many samples, many elements present in it. Okay. Now the function which we wanted to approximate it. Okay, so this is a mathematical function which we wanted to approximate it using 5-layer neural network. So like you can come up with your own function, or you can come up with your own data. You can change this function. So I strongly recommend the participants to try with the different functions. Okay. So here in this example, the function you see, like, it accepts U as an input, generates F, and it is a highly nonlinear function because we have got a sinusoidal function. You can have a sinusoidal function, square of sinusoidal function, cos function, tan function, any function. You can have a polynomial function, x to the power of 3, x to the power of 4, x multiplied by sine, in any function you can think of. Okay, and you will see the beauty of neural network capable of approximating highly nonlinear functions. Okay, so this is a f function which we wanted to approximate it. And I wanted to generate my output. My output is going to be directly not the f function that is output. I have given like the output which I am looking for in my system is like first sampling instant alone. My f1 value will be, the first value will be like, with the first value of U it enters and you will get f1 value. So that f1 value is my first value. And from the second value onwards, I've introduced a small one more mathematical formulation, but this need not be done. But this is an example which my professor used to discuss with the students. So I thank my professor. The code I have directly taken only from the professor example. Okay. And so the output what I'm looking for is like 0.1 times yp of 1 plus f of 2 is my second. And later sampling instant onwards, from the second sampling instant onwards, I'm considering 0.1 of the previous sampling instant. It's basically some kind of a dynamic model that we are aiming at. Okay, we are aiming at a dynamic model. We wanted to consider the value in the previous sampling instant. It's basically like something like a first order system which we are trying to model. So like we wanted to consider the delayed values of previous values of output also in order to decide the current output. So this is a small mathematical formulation for a dynamic modeling of this particular function along with a small extra parameter. So 0.1 times this yp, that index value, whatever is the index value, Okay, so that we are taking, and 0.6 times this index value minus 1. Because you are taking index and index value minus 1, you need at least to start with, you will start with the 3. So you need the value at 2 and you need the value at 1, previous value. That is the reason we assume the initial values here, because we need the previous values. So that means 1 or 2 sample values, previous sample values are required. So now our YP is available. Okay, YP is available. That means target labels are available. So I have got U as the input. Now I have got my target label, target output also. So for this, now I wanted to use a 5-layer neural network, deep neural network using the backpropagation algorithm. Okay. So this part is over. Okay. Now somebody has asked a question in the chat box, how we will initialize the weights. Okay. And there are no hard and fast rules available for initializing weight, except for some specific application, specific architecture. Most of the cases it is randomly chosen, and we go for some kind of a bipolar patterns. Okay, initial patterns. Okay, initial weights. Now here we see again MATLAB has got 3 RAND functions. There is a RAND, RAND, and RANDI functions. Now here in this code, the professor has used a RANDI function. Now this is basically a randomly generated data, and which will have a range between -1 to +1. Okay, so this will have a value between -1 to +1. Okay, so either -1. So like this I basically means that it will return only the integer value. If I is not there, it can take any value. Okay, it need not always be integer. So you wanted an integer value between -1 to +1. And this 50 and 1 basically, this 50 and 1 basically refers to your size of the resulting array that you're looking for. Okay, the size of the array that you're looking for. So here in this particular example, like the example, as I said, like there is an input layer which has got only one input. U is going to enter as an input. And there are 50 neurons in the first hidden layer. And W1 will be the weight connecting the hidden with input with the first hidden layer. There are 3 hidden layers. The corresponding weights are represented by W1, W2, W3, and sorry, V1, V2, V3, and W is a weight connecting your final hidden layer with the output layer. So the size of, because it is a highly complex function, what we have considered is a highly complex function, the architecture that is used is 1 neuron in the input layer, 50 neuron in the hidden layer 1, and 20 neurons in the hidden layer 2, 10 neurons in the hidden layer 3, and again like totally, yeah, there are 4 hidden layers, okay, and 10 neurons in the hidden layer 3, and finally 10 neurons connecting the third hidden layer with the output layer. So the size is like 150, 10, 10, 1. So that is the size. 150, 20, 10, 10, 1. So that you have to imagine to understand the code. Okay. So like again, as I said, like these are all random values chosen. Okay. There are totally, like you will see, we have got 5 weight vectors. Okay. Because there are 5 layers, there will be 5 weight vectors. Okay. So randomly we are initializing all the weight vectors. And every layer is also associated with a bias. Okay, so like here again, there will be, like you will see, there will be a bias for the hidden layer 1, bias for the hidden layer. Okay, input layer, hidden layer 1, hidden layer 2, hidden layer 3. So the corresponding biases are represented here, and bias is again going to take the value. Okay, it can be the value of bias. Okay, the value of bias can either be again between -1 and +1. Okay, and again, like we wanted to train the network now. Okay, we want to train the network. So for that, I'm calling a, so as I said, there is a 3-layer backpropagation algorithm, okay, which I'm calling it as a command here. But I have the code for this train multi-layer 3 is available now. Okay. But I think want of time, whether I'll be able to go through the code, like, okay. So this train multi-layer 3 needs all this information. So it needs all the initial values of weights and biases. Okay. And then we need, again, like you need to specify the parameters, like how long, what is the minimum error for which you wanted to train, and how many, what is the eta value that you're looking for, and how many times you wanted to train it. Okay. All that need to be specified. Then I think like another 10 minutes, the second speaker will be joining. Okay, this code, whether I'll be able to understand, like make you understand this code within this 10 minutes, I'm not able to be very sure. Okay. So this is a code. So this is a code, as I said, like this code is a code that that is required, okay, for the backpropagation algorithm. Uh, Okay, so the initial values of weights. Okay, and then we try to compute the output. These deltas are our deltas. Okay, and then we try to update the weights using the function of delta, all for eta, and the corresponding input vectors which are entering into each node. Whatever algorithmic step that we have seen for a back propagation, that has been written in the form of a code. Like you see the code, maybe like I think we will break for 10 minutes later, maybe like later part of today. If time permits, I'll try to complete this. Okay, because I want you to have a break now. So like you see the code here, their maximum there can be like 10 to 12 lines of code. So this complete code is a code for a backpropagation algorithm for 3 hidden layers. So like you can keep increasing more layers. If you want, you can also go for up to 100 layers. Only thing is you need to cut and copy and you need to specify how many number of neurons you want in each layer. So you need to configure the architecture. Like here we have configured, we need to configure the architecture and we need to initialize the weight parameters. We need to call our training algorithm, and the algorithm also we need to make it like more layers we have to add. Okay, and then we have to update the weights. Okay, I think if you wanted to completely understand this code, we need maybe another minimum half an hour time. Okay, let me just out of curiosity, like let me just run and show you the output later again. Okay, if time permits, we will again meet today some other time. Yeah, okay. I'm just waiting for the response to be generated in MATLAB. Yeah, once again, I'll just show you, I'll share you the response and then we will break again. We will meet one more time to discuss in detail about that. This is a very important algorithm. So I want everyone to get okay. So like you see how beautiful it is. Okay. So whatever function, the combination of sine function, what we have generated. So the blue one is what is the real one that we are looking for. The red one is what has been predicted by the 5-layer neural network with the 3 hidden layers, 1 input layer, 1 output layer. Okay. You see how beautiful it is? And by increasing the complexity of layers, by adding more neurons, like here ours is like 150, 20, 10, 10. I also tried with more layers. Okay, you can also, I'll share the code with you. I want you to add more layers and more neurons in each layer. You will see exactly it will be fitting with. Only there is a small portion, okay, where it is not exactly fitting. But by adding, by increasing the complexity, because it is so complex nonlinear problem, you may need more complex architecture in order to learn these functions. Okay, here we are like basically how to develop a deep neural network for a function approximation problem or any kind of a modeling problem. So this is applicable provided you've got the complete mathematics behind any model development or data are available, you will be able to develop the corresponding predictive model, you will be able to develop estimation model. Okay. So I'll share the code with you. You can just try. If not today, we will find some time tomorrow and we will have a detailed discussion on this code. So once you understand the code, my strong belief is that you will be able to understand any other learning algorithm. Okay, only thing is like you need to understand the little bit of max behind. Okay, so I was also in your level before I took up this fellowship, but after listening to professor, I got thorough insight into this. Okay, and so again here we have seen only about offline training. Like again, I have worked on online training. Okay, so like so that later part, maybe we will try to cover more on that. Okay, so I do not want to take up the second speaker's time. So second speaker would be logging in another 2-3 minutes. So like any quick question, like 1 or 2 questions I can answer now. So otherwise we will break and again we will meet at 10:45. Okay, for the second session. And whatever explanation which was missing, okay, this code I'll share with you. I think many of you will be able to understand the code by yourself. And once after you go through the code, if there are some clarifications, we will have a quick clarification session either today or tomorrow when we find some time. Definitely, we will discuss about that. Okay, so I want you to try for your applications. And if you can give some kind of a feedback, like whether it has worked for your application, that is very good. Okay, so that will be the takeaway from my lecture. Okay, and there are, I think there are some good questions from the chat box. So many of the questions, I think I'll be able to answer it only when I complete my discussion. Okay. Yeah. So there are questions like, ma'am, is there any, Kalpana has asked, like, is there any specific procedure available to choose the different targets? Okay. So again, choosing the target, as I said, target is a desired output that we are looking for. So that is going to be specified by the application. There is not like whether she means like how to choose a training, training data, so that part, again, we need more discussion on that. But currently, what is that we wanted to use as a target is going to be specified by the application. Okay. So how to split the data? There are a lot of methods for splitting the available data into training, testing, and validation. If time permits, we'll have more discussion on that later. And other question is there like somebody has, I think Sudha ma'am has asked a question, is it possible to assign initial weights to the neural network? Yes, I think we have discussed that the second algorithm. Okay, code, let me share the code with you. And somebody has asked for test results. Like as I said, I have shown you for a different range. Okay, you can also try for your application. Again, that is possible. We tried only for -1 to +1, but we tested for -0.1 to +0.1. It can be -5 to +5 also. Only thing is we need some time to change that. Okay. And again, like Tirumurti has asked a question, like minimization of error happens only when we back propagate. Is there any other method of propagation? Okay. So with respect to back propagation algorithm, it is happening only by back propagating it. But as I said, like we also have other algorithms, like instead of back propagating, what we are going to discuss later. Okay. As I said in my part 2 of my lecture, when time permits, we will also see like we also have methods in which through online also self-learning capability can be incorporated into the neural network. So self-learning is based on the current sampling instant also like weight update is possible. So that I think you will be able to understand only after I cover up my second part, like how self-learning online algorithms are working. After that, you will be able to understand that. And again, Sudha ma'am, there are some questions later we'll answer that. From the other participant, is it that if we design a complex neural network with more number of layers modeling application, will it results in model overfitting? Okay. So this overfitting, okay, again, there are like, we need to discuss a lot about, because this neural network, we can learn it for 1 semester. It's going to be 1 semester course. And there are a lot of things regarding overfitting, underfitting, generalization ability of a neural network. So all that lot more understanding is required. But one thing which I wanted to convey is like, if you've got only one, mathematically people have proved, researchers have proved, if there is only one hidden layer, even by increasing the number of neurons in the hidden layer, you can have only mild nonlinear problems only, you will be able to map them. Okay, so like the single hidden layer with any number of neurons in the hidden layers can learn only light nonlinearity. That means it basically approximates only linear problems, and any kind of high order polynomial functions, you will not be able to approximate them only using one layer. And for learning more complex problems, more nonlinear problems, more higher order polynomial function problems, you can do one thing is like, even if you add more neurons in one hidden layer, that is going to increase the complexity of training because it will take more time because there are more weights associated with it. So instead of that, the researchers have mathematically proved that by adding more hidden layers, you can reduce the number of neurons required in each hidden layer. At the same time, you can incorporate the capability of learning a higher nonlinear function or polynomial function. So that capability can be incorporated by adding more hidden layers with a lesser number of neurons. So this has been like mathematically proved by researchers. Okay. So why justification for deep kind of architecture? So why we need to go for a deep kind of architecture? So you can minimize the complexity of the architecture. You can minimize the number of neurons required in each hidden layer. At the same time, you can associate a highly nonlinear, higher order polynomial functions can be mapped using deep kind of architectures with a lesser complexity. Only thing is like you need more layers. So that thing that is required. So I think more discussion we will have in the data part and how to choose again. And Jay Prashant, there is one question like, do we have any thumb rule for selecting number of hidden layers for a particular applications? Okay, earlier like we have come across some thumb rules where it says like the minimum number of neurons required in the hidden layer will be like the average of number of neurons in the input and output layer. That is minimum. It is not the sufficient one, but minimum you can start with minimum number of neurons can be an average of number of neurons in the input and hidden. So that average you can start with the minimum number. Okay. And beyond that, you have to like again the number of neurons is again you need to try it with many number of neurons and you have to find out the optimum one and how to choose a number of neurons in the hidden layer. I think this I have answered your question. So I think I've answered whatever queries which